So, we begin with the topic ionic equilibrium. As such, there is no difference in ionic or chemical equilibrium. In fact, ionic is just another set of examples within the system of chemical equilibrium. If we have to differentiate between them, we may define the ionic equilibrium as a system in which either the reactants, product, or maybe both contain ions. Further, ions cannot exist in the gaseous phase, or the free ions cannot exist even in the solid. So, ionic equilibrium essentially becomes equilibrium in solutions. Before we begin, there are certain terms that need to be made clear at the beginning itself. The first amongst them, electrolyte. The substance which dissociates into ions and conducts electricity in the molten state or in solution is termed electrolyte. In this chapter, ionic equilibrium, we would be restricted to dealing with only solutions, and that too aqueous. Hence, here a bit of different definition of electrolyte is used to suit our specific need. Here, the electrolyte is a substance which dissociates into ions and conducts electricity when dissolved in water. Electrolytes are all different. They differ from each other in many aspects, the most important being the extent of dissociation or ionization. Before moving any further, let's understand these terms: dissociation and ionization. Dissociation refers to the process involving separation of ions in water, which were already existing as such in the solid state of the solute. The example, sodium chloride. On the other hand, ionization corresponds to a process in which a neutral molecule splits into charged ions in the solution. For example, hydrochloric acid, hydrogen chloride. Here, in the context of ionic equilibrium, we shall not distinguish between the two and use the two terms interchangeably. By the extent of dissociation, the electrolytes are classified in two categories: strong electrolyte and weak electrolyte. Strong electrolyte, a substance which completely dissociates into ions when dissolved in water, is termed strong electrolyte. The acids which completely dissociate into ions when dissolved in water are termed strong acids. For example, hydrochloric acid. Similarly, bases like sodium hydroxide completely dissociate into ions when dissolved in water and are termed strong bases. The salts may or may not have high solubility in water, but whatever amount dissolves is completely dissociated. Hence, strong acids, strong bases, and all the salts are strong electrolytes. Weak electrolyte, a substance which dissociates only partially, that is, marginally or slightly, when dissolved in water, is termed weak electrolyte. The acids which dissociate only partially in water are termed weak acids. The example, acetic acid. Similarly, weak bases like ammonium hydroxide dissociate only partially. Water itself shows a very small dissociation into ions. Pure water is as such a bad conductor of electricity. Hence, weak acids, weak bases, and water are examples of weak electrolytes. We have been using the terms acid, bases, and salts. Let us have a formal introduction to these terms. In chemistry, each term has a definition. These definitions are strictly followed. There are several definitions of acid and base. The very first, the definition based on observation. Acids are substances which are sour in taste, release carbon dioxide from carbonates, release hydrogen sulfide from sulfides, react with metals, the reactive metals like zinc and iron to release hydrogen, turn pink solution of phenolphthalein colorless and turn blue litmus red, the methyl orange solution pink. Similarly, the base is bitter in taste and soapy to touch. It releases ammonia from ammonium salts and hydrogen with amphoteric metals such as aluminium and zinc. They turn colorless phenolphthalein solution pink, red litmus blue, and methyl orange yellow. This definition is the easiest to demonstrate. It is the one used to give the initial introduction and distinction between acids and bases. The next is the definition given by Arrhenius. Svante Arrhenius was the first person to classify the substances as acids and bases based on structure. Arrhenius' theory, introduced in 1887 by the Swedish scientist Svante Arrhenius, suggested that acids are the substances that dissociate in water to yield electrically charged atoms or molecules called ions, one of which is a hydrogen ion, that is H+, and that bases ionize in water to yield hydroxide ion OH-. It is now known that the hydrogen ion cannot exist in water alone. Rather, it exists in a combined state with a water molecule as the hydronium ion, H3O+. In practice, the hydronium ion is still customarily referred to as the hydrogen ion. The acidic behavior of many well-known acids, for example, sulfuric, hydrochloric, nitric, and acetic acid, and the basic properties of well-known hydroxide, for example, sodium, potassium, and calcium hydroxide, are explained in terms of their ability to yield hydrogen and hydroxide ions respectively in solution. Furthermore, such acids and bases may be classified as strong or weak acid and bases depending on the hydrogen ion or hydroxide ion concentration produced in the solution. The one which easily produces hydrogen ion would be a strong acid. The one which reluctantly produces the hydrogen ion would be a weak acid. In the same manner, if an hydroxide produces the hydroxide ion very easily, it's a strong base. If it is reluctant to produce the hydroxide ion, it's a weak base. The reaction between an acid and a base leads to the formation of a salt and water. Water is the result of combination of a hydrogen ion and a hydroxide ion. The chemical formula of Arrhenius acids are written with the acidic hydrogen first. For example, sulfuric acid is H2SO4. Hydrochloric acid is HCl. Perchloric acid is HClO4. The hydrogen, which is acidic, is first. Now, moving on to the next definition, the Bronsted-Lowry definition of acid and bases. According to this definition, The acid is a substance which releases H plus when dissolved in water. H plus is the proton. These acids release proton in water and hence are termed protic acids. A base is a substance which accepts H plus from the solution. These bases accept proton and hence are termed protic bases. Bronsted-Lowry acids and bases are protic acids and bases. Let's consider some examples. The first, dissociation of a strong acid, hydrochloric acid, hydrogen chloride. When HCl is added to water, it interacts with it. Here, on the left-hand side of the equation, being a strong proton donor, HCl releases H plus while H2O, water, accepts H plus. By the definition, water qualifies as a base and hydrogen chloride is the acid. If we consider the reverse reaction, that is, from right to the left side, hydronium ion H3O plus would release H plus, becomes an acid, while Cl minus will accept H plus and will be known as a base. In the same manner, we have an example of acetic acid. Acetic acid again interacts with water to give hydronium ion and the acetate ion. That is from left to right. From right to left, the hydronium ion would interact with acetate ion to give water and acetic acid. Hydronium ion becomes the acid and acetate ion becomes the base. The case of ammonia is very different. Ammonia is not a good donor of proton. In fact, it is a good acceptor of proton. It's better than water. So, in the interaction of ammonia with water, water becomes a proton donor, that is the acid, and ammonia is the proton acceptor, that is the base. On the right side of the equation, ammonium ion is the acid, while the hydroxide ion is the base. So, that was a different example. Now, we consider the example of sulfuric acid, H2SO4. This is a strong protic acid. On the left-hand side of the equation, sulfuric acid molecule releases a proton and water accepts it. While on the right-hand side, HSO4 minus is the base. But there is a slight complication. HSO4 minus is the base on the right side, but it still has a proton, which it can release and behave as acid, giving sulfate ion, SO4 2 minus, which would be the base for HSO4 minus. The same is the case with phosphoric acid, H3PO4. The phosphoric acid initially releases the proton to form dihydrogen phosphate ion. This further can release another proton to form monohydrogen phosphate with di-negative charge. This monohydrogen phosphate can further release a proton to form the phosphate ion with tri-negative charge. These acids, which have more than one proton that can be released, they can release more than one proton, are termed polyprotic acids. Sulfuric acid is a diprotic acid, while phosphoric acid is a triprotic acid. Here we find many species such as HSO4-, H2PO4-, HPO42-, and even H2O, that is water, which accept a proton in one reaction and release a proton in another reaction. Such substances are termed amphiprotic. An amphiprotic substance is the one which can both donate hydrogen ion, that is protons, and also accept them. Water is a good example of such a compound. The water acts as both an acid, that is donating hydrogen ions, and as a base by accepting them. The protic part of the word refers to the hydrogen ions, protons, either being donated or accepted. Other examples of amphiprotic compounds are amino acids, ions like HSO4-, which can lose a hydrogen ion or to form sulfate ion, or accept one to form sulfuric acid. But as well as being amphiprotic, these compounds are also amphoteric. Amphoteric means that they have reactions as both acids and bases. So, what's the difference between the two terms? All amphiprotic substances are also amphoteric. But the reverse isn't true. They are amphoteric substances which do not either donate or accept hydrogen ions when they act as acids or bases. Some metal oxides, like aluminium oxide, are amphoteric. They react both as acids and bases. For example, they react as bases because the oxide ion accepts hydrogen ions to make water. When aluminium oxide reacts with hydrochloric acid, it forms aluminium chloride and releases water. That is not a problem as far as definition of amphiprotic is concerned. But the reaction as an acid is. The aluminium oxide doesn't contain any hydrogen ions to donate. But aluminium oxide reacts with bases like sodium hydroxide to form complex aluminate ions. Acids have basicity and bases have acidity. Basicity is the number of OH- neutralized by each acid molecule. It simply is the number of H plus it releases per unit. Mind it releases per unit, not how many it can release. Similarly, acidity of a base is the number of H plus it actually neutralizes per unit, or the OH- it releases per unit. In this case, boric acid becomes a peculiar case. Boric acid, when dissolved in water, does not release H plus. It accepts OH- from water and releases a proton from water. It is a monobasic acid, no doubts, but it is not a protic acid. It is a non-protic or aprotic acid. In all these examples, if we compare left and the right hand side in each equation, we can observe some relation. If we compare the acid on the left side with the base of the right side, or the base on the left side with the acid on the right side, we can see a relation. For example, in case of HCl, the acid on the left side is HCl, while the base on the right side is Cl minus. The base on the left side is H2O, while the acid on the right side is H3O plus. If we compare them, we find that there is no relation between the acid on the left with the acid on the right, or base on the left with the base on the right. But looking at the acid on the left and base on the right, we find that base on the right is simply the acid on the left from which a proton has been removed. In the same manner, the acid on the right is simply the base on the left in which a proton has been added. Removal of a proton from an acid forms the base of the other side, and addition of a proton to a base would form the acid of the other side. The pair of acid and base, in which acid can be converted to the base by removal of H plus, and the base can be converted to the acid by addition of H plus, that is a proton, is termed as a pair of conjugate acid and base. Hence, for HCl as acid, Cl minus is the conjugate base. Now, a question. What would be the conjugate acid of HNO3? Yes, you have heard right. Conjugate acid of HNO3. I think you are getting confused. Don't we know that HNO3 is an acid? Is the question right? Well, are we bothered if the question is right? We have to find the conjugate acid, and for that we have to add the proton. We are not bothered if the species exists or not. So strictly by definition, the conjugate of HNO3 is H2NO3 plus. Simple, strictly by definition.